Light-induced reactions. In this video, we will explore the fascinating world of photochemistry and learn how light can be used to trigger chemical reactions. Photochemistry is the study of chemical reactions that are initiated by the absorption of light. It is a branch of chemistry that has gained significant attention in recent years due to its applications in various fields such as medicine, energy, and materials science. In this video, we will cover the basic principles of photochemistry, the different types of light-induced reactions, and their applications in various fields. So, let's get started. The first thing we need to understand is the nature of light and how it interacts with matter. Light is a form of electromagnetic radiation that travels in waves. The wavelength of light determines its color, and the energy of the light is directly proportional to its frequency. When light interacts with matter, it can be absorbed, transmitted, or reflected. When light is absorbed, it can excite the electrons in the matter to higher energy levels, leading to the initiation of chemical reactions. In the next segment, we will explore the different types of light-induced reactions and their mechanisms. There are two main types of light-induced reactions: photochemical reactions and photophysical reactions. Photochemical reactions involve the absorption of light to initiate a chemical reaction. The absorption of light leads to the formation of excited states, which can undergo various reactions such as bond breaking, bond formation, and isomerization. Photophysical reactions, on the other hand, involve the absorption of light to produce excited states that do not undergo chemical reactions. Instead, they relax back to the ground state by emitting light or heat. Photochemical reactions can be further classified into two types: homolytic and heterolytic reactions. In homolytic reactions, the excited state molecule undergoes bond breaking to form free radicals. Free radicals are highly reacted species that can initiate chain reactions and lead to the formation of new molecules. In heterolytic reactions, the excited state molecule undergoes bond breaking to form ions. These ions can then undergo various reactions such as nucleophilic substitution, illumination, and addition. The mechanism of a light-induced reaction depends on the nature of the reactants, the wavelength of light, and the intensity of light. The wavelength of light determines the energy of the photons, and the intensity of light determines the number of photons absorbed. In the next segment, we will explore the applications of light-induced reactions in various fields. Light-induced reactions have numerous applications in various fields such as medicine, energy, and materials science. In medicine, light-induced reactions are used in photodynamic therapy (PDT) to treat cancer and other diseases. PDT involves the use of a photosynthesizer, which is a molecule that can absorb light and produce reactive oxygen species or OS that can kill cancer cells. The photosensitizer is injected into the patient's bloodstream and accumulates in the tumor. The tumor is then exposed to light, which activates the photosensitizer and produces ROS that kill the cancer cells. In energy, light-induced reactions are used in solar cells to convert sunlight into electricity. Solar cells contain a semiconductor material that can absorb light and produce electrons that can flow through an external circuit to produce electricity. The efficiency of solar cells depends on the ability of the semiconductor material to absorb light and produce electrons. In materials science, light-induced reactions are used to synthesize new materials with unique properties. For example, photochromic materials can change color when exposed to light, and photovoltaic materials can convert light into electricity. Light-induced reactions are also used in chemical synthesis to produce new molecules that are difficult to synthesize using traditional methods. For example, photochemical reactions can be used to produce chiral molecules, which are molecules that have a non-superimposable mirror image. In the next segment, we will explore the challenges and future directions of photochemistry. Despite the numerous applications of light-induced reactions, there are still many challenges that need to be addressed. One of the main challenges is the development of efficient and selective photochemical reactions. Many photochemical reactions suffer from low efficiency and selectivity, which limits their practical applications. Another challenge is the development of new photosensitizers that can absorb light in the visible and near-infrared regions of the spectrum. Most photosensitizers currently used in PDT absorb light in the ultraviolet region, which limits their penetration depth and requires the use of high-intensity light sources. In addition, the use of light-induced reactions in medicine requires the development of new delivery methods that can target specific tissues and cells. Current delivery methods are limited by the lack of specificity and the potential toxicity of the photosensitizers. Despite these challenges, the future of photochemistry looks promising. Advances in synthetic chemistry, materials science, and nanotechnology are expected to lead to the development of new photosensitizers, delivery methods, and applications. In particular, the development of new photosensitizers that can absorb light in the visible and near-infrared regions of the spectrum is expected to revolutionize the field of PDT and lead to the development of new therapies for cancer and other diseases. In the final segment, we will summarize the key points of this video and conclude our discussion on photochemistry, light-induced reactions. In this video, we have explored the fascinating world of photochemistry and learned how light can be used to trigger chemical reactions. We started by discussing the nature of light and how it interacts with matter. We then explored the different types of light-induced reactions, including photochemical and photophysical reactions, and their mechanisms. We also discussed the applications of light-induced reactions in various fields such as medicine, energy, and materials science. We learned about the use of light-induced reactions in photodynamic therapy, solar cells, and chemical synthesis. Finally, we discussed the challenges and future directions of photochemistry. We learned about the need for efficient and selective photochemical reactions, the development of new photosynthesizers, and the potential of photochemistry in medicine. In conclusion, photochemistry is a rapidly growing field with numerous applications in various fields. The ability to use light to trigger chemical reactions has opened up new avenues for research and development, and is expected to lead to the development of new therapies, materials, and technologies. Thank you for watching this video on photochemistry, light-induced reactions. We hope you have enjoyed it and learned something new.